Okay, this is the VCAA Specialist Maths Exam 2 from 2014, multiple choice questions, and in this session I'm dealing with questions 16 through to question 22, and these are just my unofficial solutions. So let's have a look at this question, guys. Two vectors are given, as you can see there, A and B. Looks like we've got two unknowns there, M in vector A and N in vector B, where M and N are positive reals. Okay, now we're given that the magnitude of A is 10, and we're also given that A is perpendicular to B. We have to work out what M and N are. So let's work out a little game plan here to enable us to crack the code here. Well, look at this. This is the magnitude of vector A is 10. There's only one unknown in A, which is M. So that should be easy for us to solve for that. And then when we get to this one here, that A is perpendicular to B, if we already know M, that should just enable N just to drop out very nicely for us, I would think, wouldn't you? Great. Well, we've got a game plan now, so let's go for it. Alright, magnitude of vector A is 10, and that gives us that information there. That's Pythagoras in 3 dimensions, as you know. And if we solve that, we can do that. Does that look right to you? I think so. And then we'll get M squared is 75, and therefore M would be the square root of 75. In fact, it would be the positive square root of 75, because we know that M and N are greater than 0. Okay, we've got M, guys. We're laughing. So that gets us option A or B. We've just got to zero in on whether it is A or B now. So let's do the second part of the information. We've got that they're perpendicular to each other. So we get that equation there. And that's very easy to substitute for M, as I've done there. And then just to manipulate that a little bit more, and we'll get N is going to be 5 over 5 root 3, which would be 1 over root 3. And that would be that. Now, is that there? Oh, yes, it is. It's option A today. Hooray! There it goes. So that's question 16 done very nicely. Now, if you want to do it with CAS, I'll show you over the screen how to do that. On the TI CAS handheld device, which is what we use in my school, you define vector A there, and you define vector B there. And then the norm of A is the same as the magnitude of A. So you'll find that in the menu system under vectors, and if you then put this solve statement in here, solve the magnitude of A is equal to 10 for the pronumeral M, given that you know that M is greater than 0, you'll get a nice neat little answer there. And then if you then go on to solve for the dot product of A and B is equal to 0 for pronumeral N, given that M is the result we got above, you'll get that, and you'll be laughing. Okay, guys? So that's that question done. Question 17 now. The acceleration vector of a particle that starts from rest is given by that there. Looks pretty straightforward, doesn't it? The velocity vector of the particle v as a function of t is given by, oh, that's just anti-diffing, isn't it? We've just got to anti-diff, guys, and then we'll have to put the boundary condition in that starts from rest, which means v is 0 when t is 0, and presumably it'll all just come out in the wash for us. So let's do that. There's A. Now we're going to anti-diff that now, being careful as we do that to make sure we get all this right. That looks right, doesn't it? Because cos gives minus sign for a derivative, so we're looking for an opposite sign here for this term. That's correct, that one there, because sine gives cos for the derivative, so that looks alright. And this one here is okay too. We've changed the sign and we've halved this number, so that looks good. And plus vector constant c. That's how I do them, because it's really easy to do them when you do them that way. Now, subbing our boundary conditions in, we know that v was 0 when t was 0, and therefore it looks like we get that. Just checking up on ourselves, v was 0. This term here gives us a 2 because cos of 0 is 1. This term here doesn't give us anything because sine of 0 is 0. And this term here gives us 10 because e to the minus 2t being e to the 0 would give us 1. So that gets us a 10 plus our vector c. Well, that's all right, isn't it? So therefore, it looks like c is minus 2I minus 10k. Jolly good show, and therefore, when we put all that together with our expression, our equation for v up here, we're going to get that. And what would that be? Is that there somewhere, guys? Yes, it's option D. Okay, great. That's that question done. Question 18 now. A body on a horizontal smooth plane is acted on by 4 forces. F1, 2, 3 and 4 as shown. Yes, okay. The force F1 acts in a northerly direction and the force F4 acts in a westerly direction. Okay, I think we've got that. Given that the magnitudes of F1 is 1, F2 is 2, F3 is 4 and F4 is 5, the motion of the body is such that... Alright, we've just got to work out what's what here, guys. Let's flesh this out by putting in some numbers on the diagram. Now that's looking alright, so I think we need to resolve these forces horizontally and vertically to work out what we're doing, don't you? So the sum of all the vertical forces is going to be 1, that was F1, plus 2 sine 30, that's the vertical component of F2, minus 4 sine 30, which is the vertical component of F3, and that'll be in an up and down orientation. And that comes to that, which comes to 0. So there's nothing doing vertically, guys. It's only going to be an east-west scenario we've got to worry about now. So therefore the sum of all the horizontal forces is going to be 2 cos 30, that's the horizontal component of F2, plus 4 cos 30, which is a horizontal component of F3, minus 5, and what does that come to? Looks like that. And we better get our calculators out now, which is 0.2 in an easterly direction, or else, which in other words that means it was positive. Okay, so we're looking for an easterly movement. Looks like E. There it goes, E for you and me. Yippee. Alright, question 19. A velocity vector of a 5 kilogram mass moving in the Cartesian plane is given by V as a function of t is 3 sine 2t in the I plus 4 cos 2t in the j, where the velocity components are measured in meters per second. During its motion, the maximum magnitude of the net force, okay, force, well, we know that F is ma, so we better get the acceleration and then the magnitude of the acceleration and find the maximum of that and then multiply it by the mass, and I think we'd be laughing, wouldn't we? Let's do that. There's v of t, okay, so therefore derivative required. There's the acceleration. Now, do you agree with that? Yes, I think that's pretty good, don't you? Alright, let's do the magnitude of the acceleration now. There it is. That's very interesting. Let's just flesh that out a bit more. Now, the trick with this is, I think if we take 36 of those sine squared 2t's and combine them with the 36 cos squared 2t's, that would make 36 times 1. And then we'll just get, so 36 plus some residual number of sine squared 2t's, and then we've only got the one trig function to worry about, which makes it very much easier for us. See, that's what I mean. We combine those two together, and this is what we get, guys. Right. Looking much nicer with only one trig beastie to worry about here. And of course, what's the maximum value of this term, guys? Yes, I heard you say it. It's 28, because the maximum value of sine is 1, and therefore sine squared is 1. And we get that, which is, happily, comes out to be 64 square root of, which is 8. So therefore, that's the magnitude, maximum magnitude of the acceleration, which if we multiply that by 5, being the mass, we're going to get 40 for the maximum magnitude of the net force. Is that there somewhere? C for you and me. Yippee! That's it again. Okay, great. So here comes the CAS version over the screen for you, okay, in case you're a CAS nut. Now, what have I done here? Well, I've defined this function here, the velocity, as function f1. I've taken the derivative of that and I've assigned that as f2. So now we're up to the acceleration now. Now this gets us the magnitude of the acceleration function, and I'm putting that into f3 of x. So that's what we're up to. This is the magnitude of the acceleration we've got here. Now, this gets us, this is the maximum value of this acceleration function, given that we're going from x going from 0 to pi, which would be a 1 full period. Remember, because we're dealing in 2 x's here. Okay, so that gives us the value of x. We're solving that for x. Okay, there it is. Pi on 4 or 3 pi on 4, and then if you substitute either one of those values in there and you multiply it by 5, you get 40. Okay, now that's really great, but you still need to be pretty good at CAS and thinking very clearly as you whiz through that in a CASy way, wouldn't you? Okay, so that's that question done. Question 20 now. The good old connected particles around the pulley trick. I always love these questions because they're so easy. So particles of mass 3 kilograms and 5 kilograms are attached to the ends of a light, inextensible string that passes over a fixed smooth pulley, no friction that means, as shown above. The system is released from rest, and assuming that the system remains connected, the speed of the 5 kilogram mass, or if you like the speed of the entire system, after 2 seconds is. Well, guys, these are so easy. I'll show you the Wolfie way of doing them. Put some flesh on the bones here so you can see what's happening. Now, what I do is, for the system movement, where I don't really need to be concerned about these internal forces here, in other words, they're forces with which the particles act on each other, I'm really only concerned with the external forces, which are these ones here, the gravitational forces, right? So if I draw that schematically or diagrammatically, I've got a total of 8 kilograms of mass, and we're being pulled in one direction with a 5g gravitational force, and with 3g with a gravitational force, to all intents and purposes, in the other direction, because this is trying to move down, this is trying to move the other way down, so the directions are opposing each other, which can be schematically represented just like that. Okay, so if we know that the sum of the forces equals ma, therefore we've got a net force of 2g acting this way equals ma, 8a, and therefore a is going to be g over 4. So now all we've got to do is use a constant acceleration formula to get v. V equals u plus at, where u is 0, and there it is. Okay, so it looks like g over 2, which would be 4.9, which would be b for you and me. Yippee. Again, yippee. Alrighty, question 21 now. The acceleration in meters per second squared of a particle moving in a straight line is given by, the acceleration is minus 4x. Now you'll notice immediately that the acceleration is in terms of x. This could be a case for our funny acceleration formulae, guys, so just watch out. We have to look at the boundary conditions now. If we've got boundary conditions in terms of x and v, in other words, no time anywhere, then we go back to here. Is if the acceleration is in terms of x, we use d by dx of a half v squared. If the acceleration formula is in terms of v, we use v dv dx. But in this case, it's in terms of x, so we're going to use a is d by dx of a half v squared. It's as simple as that, guys. So, if you don't know that, go back and brush up on your acceleration formulae. Okay, special case funny versions of. So d by dx of a half v squared is minus 4x. Now we're just going to solve that. Therefore, a half v squared would be minus 2x squared plus c, and substitute in our boundary conditions. We know that v is 0 when x is 5, so sub that in. Looks like c is 50, and therefore that's what we get, guys. Now, what are we looking for here? We're looking for the speed of the particle, in other words, the magnitude of v. Okay, so we're just going to solve it for the magnitude of v. So let's take that a little bit further. Substituting x is 3, we're going to get that, aren't we? Which comes to that, which comes to that. Therefore, v squared would be 64, and therefore the magnitude of v would be 8. Is that, yes, that's option A. Today, hooray for option A. Okay, done and dusted. Alright, now, last but not least, we've got the good old perennial velocity time graph. It's showing that the motion of a body travelling in a straight line, where we're dealing with meters per second, is this graph here. Okay, all right. We note that we've got a curvy bit here, so there's probably a function waiting for us as we read onwards. The velocity of the body over the interval t from 4 to 9, yes, inclusive, here we are, is given by this thing here. It's a quadratic-y thing, upside down quadratic. All right, guys. Now, we're asked the distance. Now, that's a big trap. That's a big trap. In meters, travel by the body over the 9 seconds is closest to. The reason it's a trap, guys, is because this, see between 8 and 9 seconds here, the body is turned back in the other direction because v is negative. So it's turned back on itself. So if we want the distance, it's different from the displacement because it's changed direction. So we have to work out this very strategically so we don't fall into a heap on the last question of the multiple choice. Okay, so call that area 1, that's easy. That looks like a trapezium to me. That one can be 2 down to this point here, and then this one can be 3. Now we just have to work out the sum of those 3 areas if we want the distance, remember? The sum of them. So area 1's a trapezium. That's very easy to work out. So it's the average size of the parallel sides, which were 4 and 2. That's right. Add them up, divide by 2, then multiplied by this height here, which is 9, and we get 27. Good show. Area 2 is that thing from 4 to 8, and area 3 is the same thing, but the negative of it, remember we want a positive answer here, guys, so you've got to do the negative of this integral from 8 to 9. I bet a lot of students made a mistake doing that. So, therefore, we've got to use our trusty CAS to get the answer, plug it all in, plug and chug, and it looks like we're getting 53.4375, which looks like E for you and me. Fills us with glee. And that's the end. That's the end of our multiple choice questions in Specialist Maths Exam 2 2014. Hope you got something out of that, guys, and we'll see you anon. All the best.